Hello, I'm Christian Appold. I'm research engineer at Denso Automotive Germany, working in the field of microprocessor R&D in Munich at Denso, and I'm doing a talk today now about formal verification of security properties on RISC-V processors. I will first give you an introduction into the topic, then tell you about the methodology which we use for our formal verification work. Afterwards, I will explain how our work helps to comply to security standards. Then I will present the security critical functionality which we identified and talk about the results of our formal verification. So first, a bit about Denso. Denso is a globally acting Tier 1 automotive supplier. We are one of the 3 largest Tier 1 automotive suppliers worldwide. We have a wide product portfolio from the automotive area. We offer, for example, thermal systems like car air conditioning or advanced driver assistance systems from the hardware and from the software side. Also, we offer sensors and semiconductors, for example, rain sensors, and have our own fabs for sensors in Japan. We are a Japanese company, have 165,000 employees worldwide, and we do a lot of investments in R&D. So in 2023, 3.6 billion euro R&D investments, and we have 41,000 patents worldwide. In Germany, our company is called Denso Automotive Deutschland GmbH. We are headquartered in Eching, which is close to Munich. So in the map on the right, you see our European headquarters in Amsterdam and our office in Eching. And we have in Germany 820 employees, also in other offices, but main number of employees in Eching. And yeah, this work is about RISC-V processor formal verification. We are active in the RISC-V field, are member of RISC-V International, and are developing and selling our own RISC-V processors, where we offer 32-bit and 64-bit processors. Currently, processors are ubiquitous and embedded in nearly every electronic device. So, for example, in a vehicle, there are several hundred of processors and microcontrollers. And especially for upcoming security critical applications like autonomous driving or factory automation, security is very important, as security flaws which are exploited can have drastic consequences. On the other side, in the past years, several famous bugs and security vulnerabilities in processors have been found. For example, the Intel Pentium bug in the 1990s and Meltdown and Spectre more recently. And design flaws in processors can be exploited by attackers with drastic consequences, for example, causing accidents in autonomous driving and harm even people in the worst case. For this reason, already in the pre-silicon phase, reliable verification of security critical functionality of processors is needed. Traditionally, simulation is used in hardware development for verification in industry, where a processor is stimulated with a set of input patterns, and then the system response is investigated if it's according to the expectation. Problem is that you cannot trigger all possible input patterns from the efforts, and due to these reasons, corner case bugs can be missed. But as security is very, very important, we suggest and say formal verification is required for security critical functionality. And in this work, we investigated how to perform this formal verification with Jasper, formal verification tool Jasper from Cadence. And RISC-V instruction set architecture is open. It's available for everybody. Everybody can look into it, can investigate it. That's why we are saying RISC-V processors are targeted by attackers easier due to openness of the ISA. And additionally, the dispersion of RISC-V processors is strongly growing. The market forecasts say that dispersion will even grow much more in the future, and RISC-V take more market shares. And also several small companies exist which don't have the verification infrastructure from, for example, bigger companies like ARM. And for all these reasons, security verification guidance is urgently needed for processors. And there's no previous work which did a detailed analysis of RISC-V specifications for security critical functionality. And this gap we close with this work and do several contributions. We identified a large set of security critical functionality for RISC-V processors from the specification documents. From this, we derived properties for proving the correctness of the security critical functionality. And then we optimized the use of Cadence Jasper tool for verifying the properties. We identified a lot of properties, and our full property set can be found in a paper which has been published 2023 at MemoCode conference. And this paper is called there Form Verification of Security Properties on RISC-V processors. And when you search for it in Google, you will find the paper and all our properties and can read about them. Then to our methodology, we have some manual steps, some automated with manual, and some automated steps in our approach. First step is manual identification of security critical functionality from specification. We looked through the RISC-V specification documents, unprivileged specification, privileged specification, debug specification, identified security critical functionality, and we also looked into the technical reference manual to our processor. Then we modeled properties, proving security critical functionality correctness in system Verilog assertions, and did use this as an input for the Jasper FPV form verification app to formally verify the processor RTL of our 32-bit processor used in this work. Then we investigated the verification result. If the properties are fulfilled, we have compliance with specification and microarchitecture intent. If not, Jasper outputs a counterexample, and we analyzed it using the Jasper visualize and why functions, which help with some automatization. And also we did then manual analysis. Then if we identified a design bug, we found the non-compliance with specification and microarchitecture intent, and the RTL needs to be fixed. If no design bug, there's a problem in the property modeling, the property needs to be reconstructed, and then the form verification of the processor RTL be done again. How did we find our security critical functionality? First, we looked into the RISC-V architecture for protection mechanisms for security. For example, there's the physical memory protection, which offers some memory protection regarding allowed operation, like read or write accesses for memory regions. This is security critical functionality. There are some other security protection mechanisms in the RISC-V architecture. Also, we looked into existing malicious attacks from literature and identified processor functionality which is involved there and can be classified as security critical. For example, we looked into the paper SOK Eternal Void Memory from 2013 and found there some security critical functionality. Also, we identified an approach to enumerate possible other new attacks which could be done, and identified there also security critical functionality from these attacks. As mentioned, our work helps to comply to security standards. I will now talk about 2 security standards where our work helps complying to. There's the common criteria, which is an international standard for independent security evaluation and certification. It is for IT products implemented as hardware, firmware, software, and the standard has 7 different levels of evaluation, which have different requirements to comply to these levels, EAL1 to EAL7. And the highest level of these levels is EAL7, and it requires formal methods for design and implementation verification. This is the highest assurance level, and it's for extremely high-risk environments where utmost security is critical. So in general, common criteria requires formal verification when utmost security is critical, so in high security areas. And our work gives guidance how to do this formal verification for security critical processor functionality and helps with this to comply to this standard. Then there's the common weakness enumeration. Another standard, it's a community developed list of common software or hardware weaknesses. And for hardware, it lists weaknesses around concepts that are frequently encountered in hardware design, so concepts that are seen often in hardware implementations, and where it mentions weaknesses in these concepts. And there's also an overlap between the weaknesses described in CVE and our work. The RISC-V specification describes what functionality should be implemented and how the functionality should be implemented, and some of the functionality protects against CVE weaknesses. And as our properties prove security critical functionality from the RISC-V specification, our properties prove that this security critical functionality is implemented correctly and protects with this against CVE elements also. And an example CVE category where our properties help protecting against issues is the privilege separation and access control issues category. For example, there are subcategories incorrect default permissions where our mode transition and exception and interrupt property categories where we, for example, prove default mode settings for exception interrupt help to comply to. Also, we have improper isolation of shared resources on a system on a chip category, and there help our CSR debug operation, mode transition, and PMP properties to comply to. Then to the identified security critical functionality, we identified quite some properties of security critical functionality and grouped it in 9 categories. And our properties can detect bugs in the hardware. And if these bugs would not be fixed, malicious behavior exploiting them can be triggered by attackers by software execution. And with this, several security issues could happen. So there could be a change of functionality where the program behavior is changed. There could be a change of control flow. For example, a branch to attacker code, and the attacker could execute its attacker code. There could be a denial of service, which means that the program does not do anything useful at all during its execution. And there could also be privilege escalation, for example, raising the privilege level of a processor and allowing normal users operations which are not allowed for them. And on the left, you see a figure with all 9 categories of security critical functionality, and for each category also the security issues are mentioned there. First category is instruction execution. We check here instruction flows through the pipeline. So for example, if an instruction moves between 2 pipeline stages, it is not changed. And if an instruction stays in one pipeline stage, it stays the same. We have the CSR category where we check that compliance with CSR access rules. So for example, we have CSRs which are allowed to be written only in machine mode, and we prove with these properties that they cannot be written in user mode. We have the debug operation where we check compliance with debug CSR access rules. For example, there's a debug program counter where the program has to continue after debug mode. We prove here that this CSR is written correctly. We have the exception interrupt category. We prove here, so proper handling is required, and we prove this. For example, some status bits, some status information has to be stored at interrupt exception execution, like, for example, the privilege mode when entering an exception, or also the program counter for this, and we prove this with these properties. There's the mode transition category. We prove here, so there are several privilege modes specified in RISC-V specification, and we prove with this category that mode transition rules are met according to specification. We have the PMP category, which is a memory protection implementation, and this specifies access control rules for memory regions that need to be met. And we prove here that this, according to the configuration of the PMP, the memory access rules are met with corresponding properties. We have the control flow category. The correct setting of the program counter is very important, and we prove here for each setting of the program counter that it is set properly. We have the register update category. We check that the correct target register is updated, which means that if a register changes its value, that is the register targeted by the executed instruction. And the memory access category proved that value and address of memory transfers is as intended. For example, for store, that the value in the register is transferred correctly to the memory as intended. Then I have 2 examples of properties. Both with both we have found bugs, and for example, one is from the control flow category. We prove here the correct setting of the program counter. Each program counter setting is verified, and it's verified at writing the program counter into the right backstage pipeline register. So each instruction which reaches there, the program counter is verified for correctness. And there exist several possibilities for setting the program counter, and we have one property for each. For example, for the reset program counter, for standard program counter increment, which is in our processor program counter +4, for interrupt occurring, exception occurring, and program counter set due to last occurring instruction, for example, jumping link register, and branch, and others. And possible security issues that can happen when they are not checked. We can have a change of control flow. For example, the broken counter can be modified to jump to attacker code execution, or we can even have denials of service, for example, disabling proper instruction flow at all. In the property example is a correct broken counter after the mred instruction. This is failing, and we found a bug. And yeah, we have the assert statement here given. For example, in this property, a precondition is if we have not the first instruction, we write into the write back pipeline register, and the last instruction was an mred. Then we prove that the instruction program counter which goes to the write backstage pipeline register is the broken counter from the MEPC register, and MEPC stores the wrap return PC to which the PC has to be set after an mred. We found a bug here. I'll explain later more a bit about it. We have the control and status register category, and the properties check compliance with control and status register access rules. There are also several security issues when not checked. There could be a change of control flow. For example, the broken counter for exception return could be modified and jump to attacker code. There could be denial of service when, for example, interrupts are permanently disabled in the corresponding register. And there could be privilege escalation, for example, modifying the stored previous privilege level and then jumping to a wrong privilege level. This property is also failing. We found a bug. And this for an example property, which is shown here. And this property is that CSR write access is only done for CSI instruction with register and immediate operand. It's shown in a table. So you here see a table above right with CSI instructions, and then for certain values of, in principle, for 0 value of register, target register, or RD, or source register as1, or immediate operand value 0, read of CSR, write of CSR is not always possible. And we have here an example property down for status CSR, which is also used in this way for other CSRs. And if we have a CSR instruction and additional conditions are fulfilled, it's not valid. Then the write enable from status register is not allowed to be high because, for example, if the additional conditions are not fulfilled, the write enable the write should not happen in the conditions mentioned in the table, and this property was failing in our experiments. Then to our form verification. We executed the verification on a 16-core AMD server with 2.2 gigahertz and 128 gigabyte RAM. All verification runs have been executed with our own RISC-V processor core as top-level module and some information about the design. It had 84,000 gates and 49,000 RTL lines. We did one Jasper verification run for each property category, so in principle 9 Jasper runs, one for each category, and all properties in the category verified in parallel by Jasper. Jasper in general contains formal verification engines for foolproof and bug hunting, and we used several different of the engines in parallel for verification run to be able to benefit from the different advantages which the engines have, and we let Jasper choose automatically the most suitable engine. And we identified in total 1,146 properties and grouped them under 9 categories. We achieved foolproof for all passing properties, and the runtime for the properties were often regarding control flow properties. We need to apply black boxing abstraction, but with this of some modules, but with this we could prove the properties below 24 hours. And for other properties, we had a runtime of less than 4,000 seconds, and we found 3 design bugs in our work. And here's an overview about the property categories and the number of assertions in each category in the assertions table. So in total, 1,146 properties. Also, we show the failing properties. We have 2 bugs for the CSR category, but we have several CSRs, and they appeared for some of the CSRs, so it sums up to 114 fails. Bug 1 is violation of specification, no read to the CSR for CSR instruction when the target register is register 0. So as shown in the table on the CSR properties slide before, this was violated. There was still a read possible. We have another violation of specification, bug 2, no write to the CSR for CSR instruction when the source register is register 0 or the immediate operand is 0. This was also violated. And bug 3 is the wrong broken counter was taken in debug mode when the mred instruction was in the right backstage. And an exception occurs as in debug mode, the MRET instruction successor PC should be executed, but the processor jumped to the exception program counter. That is conclusion, proliferation of RISC-V processors is strongly growing, and if more RISC-V processors are in the field, we expect they are more investigated, they are more targeted by attackers, more investigated, and that's why we expect that the number of discovered security vulnerabilities in them will grow. And for this reason, methods to ensure high security level are urgently needed. For this reason, we did this work and identified, categorized, and formally verified a large set of security critical properties for RISC-V processors. Formal verification scales well for our property set. We could prove, including black boxing for some properties, that all properties can be verified in less than 24 hours. And we identified the design bugs which have not been found by other verification approaches which our processor team applied. Generally, our work is guidance for RISC-V security hardening. We verified the security critical functionality and could, with this, avoid bugs in implementation of the security critical functionality, which could be exploited by attackers for attacks. And this helps to significantly increase the security level of RISC-V processors. And the properties and presented security formal verification is used in our processor development. This was my talk, then thank you very much for your attention. And if you have any questions, please reach out to me and contact me. Thank you.